Yeah, so we allow for specific kind of pipeline structures where at the very beginning of every pipeline, we're going to have the data set coming in, of course, right? You can't do machine learning without the data. And then each step here applies some sort of transformation to the data and then passes it on to the next step, right? So here, in this pipeline here, it's going to cast the data set in polynomial features and then pass it here. Here we're taking another copy of the data set, a separate copy, applying PCA, and then we combine all of those features into a single data set, do some feature selection, and then finally model it, right? In this split here, you use trees. You know, if you're a computer scientist, you know that we absolutely love the tree structure. Yeah, that's where the tree-based part comes from teapot. Just fun fact. So we create pipelines, and then we let the evolutionary algorithm, or this evolutionary process, optimize them. So I'm just going to show some of the basic operations of how this works. So if we have two example pipelines here, the one is very simple. It takes the data, passes it to a random forest classifier. Another one takes the data, scales it, and then passes it to a logistic regression. The algorithm can do things like an insert mutation or an insert change, where it can insert new operators into a pipeline. It can do a shrink mutation, where it deletes operators from the pipelines. It can do a point mutation, where it changes an existing operation to a different one. So you'll note that I just changed the polynomial features to PCA. And the point mutation can also change the parameters. So this is how we tune the parameters of the models and everything. And then we have this concept of crossover, which is basically we can take two pipelines and sort of have them electronically swap spit or electronically swap their DNA. So you'll see that between the last two here, that the two pipelines swapped their models. Right, so this allows them to sort of exchange maybe partial solutions to a problem or something like that. And of course, since we're mimicking evolution in the computer here to do this optimization process, we have a whole population, or a whole bunch of pipelines that we're considering simultaneously, and they're all different, even though I was just lazy and copy-pasted the same one here. And then we perform a multi-objective optimization procedure on it. Basically, we're telling the algorithm, as it tries out, as it applies these mutations, as it applies this crossover to the pipelines, when it's evaluating them, we evaluate it based on accuracy. Right? So first we want an accurate model, but we also say maximize accuracy while minimizing the complexity of the pipeline. Where the complexity of the pipeline is the number of operations in the pipeline, right? So we want maximum accuracy with simplest pipeline possible. These are all like fairly standard techniques in the field. And of course we made this into an open source tool. So if you just Google TPOT, it'll come up on Google. And you'll find this, so we have it on GitHub. You can look at all the code right now if you wanted to. And actually what I'm about to show is a live demo. So we've also released this as an actual Python package. If you're familiar with like Anaconda, we're working on getting it onto there, so you can Conda install. But right now you can just use pip to install it. So let's maximize that. You see the text okay down there? Yeah, good. So you would basically just go on your command line, pip install teapot. I already have it installed. The latest version should be 0.6.6 or something like that. We had a lot of bug fixes in this release. But anyway, so you can use it on the command line by saying teapot, and then if you want just the basic commands, we have tons of parameters for this, right? And like people have just requested features, so we've added way too many features now. But okay, people are happy with it. So you can use it on the command line, or if you're familiar with scikit-learn, we actually have an exact same interface as most of their supervised learning models do. Right? So you just say, create an instance of teapot classifier, and that will drop in and replace a random forest or whatever you're currently using. Here I'll just show the command line version and just show you how it works on an example problem. So here's the command, which I'll type it out and explain it, I guess. But you call it on the command line by typing teapot. This is sort of like using less or man or cd or whatever else. It's just another command once you install it. And then I'm going to run it on teapot. on a data set, CI data. So I'm going to run it on that noisy Hill Valley data set that I showed you earlier. That's just what I'm pointing to, that data set there. What other parameters? You can change the verbosity of the program, so by default it doesn't print out very much to tell you its progress and everything. But if you set it to 2 or 3, it'll spit out a lot so you can see things happening, which makes me happy at least. I'm going to give it a max time of 5. So there's 2 different ways you can specify how long it runs. In evolutionary algorithms, we can specify like generations and population size, and basically that's how many pipelines we evaluate. Or you could just say, hey, I've got 5 minutes before I have to turn in my machine learning homework, so you've got 5 minutes to solve this problem. And I'm also just going to change some other things. So you can change the population size. I'm just going to set it to 20, so it'll run decently fast. And then I'm going to do -O and give a Python file name, although this can be any file name. I should run this in a different directory. But anyway, and this will, after it finishes the optimization process, it will output the corresponding scikit-learn code for you. So all you have to do is specify the input file, and boom, problem solved. And so we've put in a lot of work to make this a really nice, really easy to use tool. Okay, so let's go ahead and run it. Good. Okay, so it's in verbose mode right now. So it's going to show you progress as it's evaluating things. Would it help if I turn the light down, or can everyone see it okay? It's okay. All right. Cool. So yeah, so we use one of these nice, Python progress bar things. Yeah, it helps a little bit. Thanks. So it's going to show, and sometimes it'll sit there evaluating a pipeline for a while, because sometimes it just decides to try out a really complex one that takes a while to evaluate. But basically, what this is doing is it's creating machine learning pipelines, trying them out, and then taking the best ones that it tried out and building on top of those. And doing this iterative process of trying to continually build a pipeline that maximizes the accuracy on the data set that you give it and minimizes the complexity of that pipeline. All right. So at this point, I guess I can actually just take questions. It'll print. It's doing cross-validation and everything in there to evaluate the data set. I guess it's already solved the problem decently well, but I'll let it run for the full 5 minutes, unless no one has questions. Does anyone have questions so far about Teapot while this runs?
I have a question about the algorithm. When you showed that you used to solve the game Worsley Waddle.
Sorry?
To solve the game Worsley Waddle.
Oh.
So obviously I don't know the game. But I was wondering, it looks familiar. It looks like you are trying to find the shortest path in a graph.
Yeah.
So I was wondering how the algorithm you use is different from first search algorithm.
Well, so the algorithm that I'm using is it's how should I say it? In that problem there, it's basically generating a whole bunch of random paths at first, and then it takes the shortest paths and then makes small alterations to those paths. So maybe connects 2 different nodes or something like that. So it's sort of this iterative, building, tinkering process that the algorithm is following. Although of course there's some way better algorithms for doing that, but it was a toy problem. So. Yeah. We can talk more about it offline too if you're interested in evolutionary algorithms. But yeah, basically the idea is it's continually trying to build off the current best solution rather than enumerating all possibilities or anything like that. Sure.
So when you were looking at time series data and comparing to random forest regression,
Yeah.
What sort of pre-processing methods would you use to improve the performance of random forest? Like, would you maybe consider the relative position of points compared to?
Yeah. We'll see what Teapot recommends. But yeah, it certainly seems like PCA. PCA helps with that, and also just trying to get at. In that specific problem, it's often important to, you're sort of looking for interactions between the time points, right? You want to see if this one is low and maybe this one is high or it's lower or something like that. So you can think about some manual feature engineering that you want to do there. You could get really fancy with it, but I usually just try to use the existing stuff.
Okay. So I have one more question then, and that Sebastian, at your talk, you recommended contributing to GitHub repos. What problems could people here work on for the Teapot repo? Is there anything that they
tons. Yeah, we have tons of issues on there. Yeah, I'll have a link to the repo at the very end of this talk too. But yeah, basically, if you know, it is premature, but if you're interested in getting involved in an open source project, Teapot's a great one to jump into because we're doing Python, we're doing machine learning, and we have tons of simple little things like adding these nice features that I was just talking about, like a time limit. But we also have some more like advanced research projects if you really want to get into the nitty-gritty of what a machine learning research project looks like. I've been very adamant, and thankfully my boss has been supportive about doing all of this online and on GitHub. So literally, if you go to our issues on the Teapot repository, you will see, I would say, 98% of what we're thinking about and what we're doing with the Teapot project. And the other 2% is just because I've been too lazy to log them on there, and we will eventually. But yeah, so if that is of interest to you, then absolutely reach out or even just look through the issues and see if anything looks interesting, or email me. My email will be listed there. Oh, it didn't do any cool pre-processing this time. Okay, so anyway, it looks like it finished. That was a quick 5 minutes. And so what it does is at the end of the Teapot optimization process, it'll tell you what the best pipeline is. So this, I guess it wanted to use SVM, linear kernel, and it'll give you your cross-validation training score. Right, so this is the training data that it used, and it'll give you the holdout score. So this is how it did on unseen data in the past. So it did an okay job. And as I said, what did I name it? Demo.py? Yeah. Please zoom in. Oh no. I'm going to be one of those computer scientists who can't solve something simple in a presentation. Oh well. Anyways, you can kind of see the code. There you can just
control scroll.
Control scroll, maybe.
Control scroll. No. Control plus looked like it was doing something, but someday. Anyway, if you run, I guess another thing you can do. What's that?
This makes it into a word processor.
Yeah, I guess.
I think there's a little drop down at the very bottom. See 100%? No, that's probably not it.
Oh.
Yeah.
There we go. You can see the code much better now. Yeah, so it prints out, pretty decent Python code for you. And all you have to do is fill in, where your data file is for direct from CSV command, whatever column separator you use, whether it's tabs or spaces or commas or whatever else. And then it will run that pipeline for you. All right, so like I said, you literally can use this to do your machine learning homework. Of course, don't tell your professor. Whenever I give this talk to like companies or whatever, I always say if this earns you a ton of money, at least donate like 5% to the project or something, because it's entirely possible. One thing I will note with this is, it found a decent solution to this problem in 5 minutes, but just to set expectations and to point out what it's really doing here, with larger data sets, it's going to take much longer, right? If you want to run this on the MNIST data set that has 60,000 training images, it's probably going to take several hours. So just be patient, just set it running and go play a video game or get coffee or play soccer or whatever you want to do. Let it do the work while you can go off and do other things. So, yeah.
I have a question about the output of your Teapot. What's the final output of the Teapot? Is specifying the component or what is called the operations or the pipeline?
Yeah, exactly.
Optimized
Yes.
pipeline?
Yeah, so we actually, yeah, we do the whole thing. We write code to read in the data for you and to actually do the cross-validation for you too.
So has been generated automatically by...
Yeah, exactly.
Okay.
Yeah, so basically we have a program that takes the data set, automatically, finds a pipeline for you and then writes the code for you afterwards. Yeah. Which that was an interesting task, writing code that writes code that writes code. But that's the kind of fun stuff we do in academia.
Next issue would be making it PEP 8 compliant, right?
Yeah. Hey, if you wanna go after that. Yeah, it's not fun trying to make generated code PEP 8 compliant, but it's PEP 8 compliant-ish.
Well, lizards in the office.
Yeah, good. Yeah, I mean, I guess there is auto PEP 8, right?
Yeah.
It's automatically does it for you. Anyway, yeah, so here's where it actually, which, by the way, if you're not familiar with the pipeline object in scikit-learn, it's really amazing. It makes it really easy to chain machine learning operations. So check that out if you haven't already, or just let Teapot write it for you. Anyway, we had a question here.
Did you specify what the target was when you actually ran the Teapot?
So that is that's a parameter. So you can just say, target is class or whatever else. By default, the target is class. And the data file I used already had the class label named class, so I didn't have to specify it. But if you have a different name, like, target or C or whatever you want to call it,
Right.
you can just specify it there and it'll use that column.
How does it know what to use as like a performance metric? Because what if it was just doing like labeling everything as true, and then you could say, well, I got 99% of the things that.
Right. Yeah. So by default we use a version of accuracy that sort of like scales for class imbalances. But basically we're using accuracy by default. But there's also another parameter where you can say, shoot, I'm going to have to look up the docs. We've added so many things. Wow, this is a mess. It's still a mess. Oh, here it is. Wait. Scoring. There we go. So if you're familiar with like the cross-val score method in scikit-learn, any of those, you can pass basically any scoring method. So if you want to use like, let's see, it's scoring function or something like that, you could say ROC, AUC, or whatever else.
Yeah.
You can choose whatever metric you wanna optimize.
And then could you tell it to do like K-folds or whatever for each
Yeah.
one as well?
Yeah, I think it's like -num_k or something. It's in the docs, but yes. By default it does 3, but you can specify as many as you want.
Yeah, related to Zach's question, you showed us a classification example. Does it also support regression?
I'm glad you asked that, yes. So, yes, you can also pass it a regression problem. And you basically, when you're doing it on when you're coding it like a scikit-learn model, you would just create a Teapot regressor instead of a Teapot specifier. On the command line, you say, it's like mode regression or something like that, and boom. That's all you have to do. It's suddenly doing regression. Eventually, we'll add like, multi-label and clustering support and all that stuff, but we kind of want to do it. We're in science mode right now. So, yeah.
We talked a little bit about like pre-processing your data, and I'm guessing, I wonder a bit about how this handles like really funky data sets, things with like missing values and autocorrelated all the hell.
Yeah. Right, so like all scikit-learn models, it does not handle missing data currently. Although that's what I was talking about, we're slowly trying to expand into that data cleaning phase.
Right.
So we are going to add like imputers to it. But yeah, I mean, there's certainly some data sets that completely fool it. We found them, we're always trying to poke holes in this thing. So yeah, that's I guess tough to say in detail because there's a lot of problems out there.
But is there like any specific sort of like data that it's just like painfully bad at handling, like, things are, unbalanced or autocorrelated or any of the various data problems that I, encounter, or like,
Yeah, right.
are any of those issues, or no, it's like, well, just
I mean, it's
figure
pretty,
out the pre-processing step for this, like.
yeah, I mean, it's pretty good. I mean, some problems it sometimes struggles with are just problems that are commonly struggled with in machine learning, right? Like, ultimately, this is a meta-optimizer over the existing machine learning algorithms. So we work with data sets, for example, that are simulated where either of the, like, let's say there's two features that when you combine them together, they're highly predictive of the outcome, but individually, they're actually like worse than chance, or basically chance, right? That's very hard for a lot of standard machine learning methods to pick up on. Sometimes Tplot struggles with that, although we've been adding some of our own sort of custom methods to be able to handle that as well. So, yeah, that's the biggest problem I would say that we've seen struggle with so far. And of course, if there's any missing data, it crashes. But we also have, you know, if let's say it generates a really bad pipeline, or you put in some really bad data, we actually have a catch-all in the optimization process to where it won't fail on you in the middle of it, right? So if it, let's just say, generates a bad pipeline or something like that, it'll just throw it out and move on. So that was something that frustrated me that we didn't have early on, that we quickly fixed.
Hey Randy,
Yeah.
are you almost out of the presentation? So
Yes, maybe I should just wrap up, yeah. Okay.
I mean, you can go on question.
Well, I mean, we can do questions again afterwards. I'm basically at the wrap-up stage, so yeah. So yeah, basically with Tpot, you know, at first this was basically a feasibility study, you know, right? Like I was certain that, you know, we could use an evolutionary optimization method to automate machine learning pipelines, and it seems that yes, we can to some degree for many machine learning problems. I'm not going to claim that Tpot solves all problems. But it solves many machine learning problems out there. We've benchmarked it in hundreds at this point. And what's especially nice about it is that we don't have to have user input, right? So you could fire up an instance of this, let it run, and then hopefully it'll find a good solution for you. You can even run multiple instances, right? You know, that's one nice thing about computers. They work endlessly. They don't need food. They don't need sleep. They just need electricity and not to overheat. Another important thing to point out with Tpot is that we really view it as a data science assistant. You know, so I've had people, I think jokingly, asking me, like, "Oh my gosh, I'm getting into data science. Are you trying to put me out of a job that I'm not even in yet?" And I say, no. You know, Tpot is meant to be an assistant. Right? You know, it's something that you maybe fire up a few instances of on the side when you initially approach a data problem, but then continue your normal workflow, come back the next day and see what it recommends to you. You know, so hopefully it can be a time saver with, you know, the parameter optimization process. Maybe it can even, you know, because it's not limited by sort of our normal human intuitions, it can find a really interesting way to analyze the data. It can find an interesting solution, so it can be an idea generator in a sense. Another important thing to point out is that Tpot isn't really meant to be like a new machine learning model. You know, every single time I see a new machine learning model, or I see a new programming language, I groan and I say, oh, another one I have to learn. That's not the point here. The idea here is Tpot encapsulates all of the machine learning models out there, all of the feature engineering methods out there, right? So if you say, well, I think deep learning or ANNs or whatever else are going to perform better, well, great, let's put it in there. Which, as a side note, we had a summer student do that, and it's god-awful slow. But anyway, yeah, deep learning. Which actually nicely segues into one of the major limitations that I want to stress again with Tpot, is it's going to be very slow in large data. Right? If you have a large data set, expect it to run possibly for days even. But if you're just patient with it and you let it run in the background, eventually it'll find something for you. If you get really impatient, you can just Control-C or interrupt and it'll give you what it's found so far. And also the search process is still fairly ignorant, right? Like all these little changes I was talking about, mutations and crossover, they're random, and probably we could guide that a little bit better, you know, because we have some knowledge about what makes good machine learning pipelines, so maybe we can bias that process.